Sorry, I'm not able to be in person, but I look forward to all the talks and the discussion. So I'm going to talk about some work we did at Commerce Labs on candidate differential privacy algorithms for the so-called Group 2 products for the Decennial Census. This is in collaboration with a lot of people at Tumult, MITRE, and the US Census Bureau, but in particular with Sam Haney, William Sexton, and Amrita Pai from Commerce Labs. Okay, the first disclaimer. So we've been contracted to develop candidate algorithms for the 2020 Decennial Census Group 2 products, which I'll be talking about soon, but the US Census Bureau has not decided to use these algorithms yet. In order to assess these algorithms, we consider candidate accuracy targets at corresponding privacy loss budgets, which I will be showing you, some of which are set up in consultation with the US Census Bureau SMEs. Again, no determination has been made by the US Census Bureau about either the accuracy targets or the privacy loss budget. These are just sort of for demonstration only. Okay. So before I go into the data products, I want to say a little bit about what methodology we use for deploying differential privacy for these data products. We believe that we need to engage with stakeholders early in the process so that we can successfully deploy differential privacy and release good, useful data products with strong privacy guarantees. And so we started out by talking to the internal stakeholders who in turn have been talking to external data users to elicit requirements. What are the privacy and accuracy requirements? What kind of tabulations do you need to be created? And developed a prototype algorithm, which was a rough algorithmic strategy to answer these queries. And then we identified what parameters in these algorithms affect the privacy and the accuracy or the fitness we use. And so we used these, and then we interactively with the stakeholders did something called privacy negotiation, where we visualize these privacy utility trade-offs and help the stakeholders think critically about how to set privacy loss budgets, how to think about these algorithms, and so on. And once you have done that, we finalize the algorithm, give the parameters, and deploy differential privacy. Okay, so today I'm going to talk about two data products in these Group 2 products. One is called DHCA, which is detailed race and ethnicity data product. And the second one is called Supplemental Dhc, which have tabulations about persons and households. Okay. In each of these cases, I'll talk about the problem, the requirement, and then show you what the candidate algorithm is. And that should give you a sense for what noisy measurements are being generated in each of these data products. Okay, so what is DHCA? The goal here is to release a total count and a sex cross age pyramid for different population groups that are grouped by geography and what is known as detailed race and ethnicity. So you have many tables. Each table has a total, account for gender, and then account for gender cross age. And each table corresponds to people in a population group. So a population group is a pair, is a geography and a detailed race or ethnicity. The geography could be something like a state like North Carolina, or a county, or an AIAN region, things that Ryan and Michael talked about before. Detailed race or ethnicity is something that is more detailed than white or black or Hispanic and so on. These could be like very detailed tribes like Aleut or Japanese and so on. Now, every person record has several attributes. So it has a geo record, which usually corresponds to a block, and that determines a mapping to several geographies. And then it also has several race codes, race and ethnicity codes. And these race and ethnicity codes determine mapping to up to 18 different detailed race and ethnicities. So a race code could say this person is Japanese, but also Korean, in which case they will be tabulated under Japanese alone, they'll be tabulated under Korean alone, as well as under Japanese alone or in combination. Okay. All right, and so each person may result in counts for multiple tables, and then that count increases by one. Okay, so that's basically a summary of what the tabulation is. This is a pretty detailed tabulation. So you want to tabulate statistics for all 350+ million persons in US and Puerto Rico. And the output is a sex by age pyramid, which could be up to 46 counts, that are released for over 3,000 geographic entities, if you count only the US, the state level, the county level, and AIA and NH areas, or 3,000 to 4,000 race characteristic iterations, which results in like close to 500 million output statistics. In fact, now they're also considering tracts and places, which adds another close to 100 million geographical entities. And so it'll be an additional 10 billion statistics if they want to do that as well. So it's a very detailed data product. So I want to talk a little bit about what are the key fitness for use criteria here. So we care about keeping relative error low. So if the statistics are large, then they could support higher error in them, but you don't want to release statistics with very high relative error. Even though the goal is to release a sex by age pyramid, like, whether we publish them or not, users are going to try to derive intermediate statistics like the sex marginal, right? One other goal was to have the error for these release statistics predictable. So they wanted to make sure that you must be able to understand what the error is, and the release statistics must be integrated. Beyond that, there were no other consistency requirements for this data product. Like, for example, the state counts don't need to add up to the total US count and so on. Okay, so I'm going to start describing a simple algorithm and then show you a sequence of optimizations, partly because that's sort of how we approach. We started a simple algorithm, spoke to stakeholders, and based on conversations, we were able to optimize this algorithm. The simple algorithm is very straightforward. You generate each statistic, and to each statistic, you either add noise drawn from a geometric distribution, which gives you pure differential privacy, or you add noise using a discrete Gaussian distribution, which gives you zero concentrated differential privacy. And these are things that you've seen before, right? Each person's record contributes to up to 144 different statistics, and so you have to add noise calibrated to that sensitivity. Okay. So the first optimization here is like different population groups have different sizes, right? If you're looking at a large population group like European, and they're looking at what is the total count of Europeans at the national level, that's going to be a large count, right? So you can potentially allow for more noise there. And so you could provide a portion less of your privacy loss budget at that level. Whereas if you look at a detailed race group like Egyptian in like a small county, then you probably have smaller counts, and so therefore you want to spend more budget so you get less noise, right? And so this allows you to sort of trade off noise, but at the same time get similar relative errors across all of these population groups. The next optimization is like to only compute the most detailed statistics and then aggregate. So again, like rather than spending privacy budget for computing the sex marginal as well as the sex class age marginal, we just compute the sex class age, and the sex can become constructed, a sex marginal can be constructed by aggregating these counts up, which is fine because even though the error is higher, when you aggregate noisy statistics, these counts are anyway larger, so they can allow for these higher errors. The key optimization that we did was what we call adaptivity. Remember, we had half a billion statistics, even if we just focused on the nation, the state level, the county level, and the AIA level. That is a lot of statistics, given that we're only starting with 50 plus million persons, right? And so therefore, what's going to happen is some population groups are just going to be too small to support very detailed sex plus age statistics. So what we do is we decide based on the size of the population group whether to release a very detailed statistic or something that is coarser. So the way we do it is the following. So we use a fraction of the privacy budget to estimate the size of each population group. And then we have these levels of statistics. Either for each population group, we decide, should we only release the total? Or should we release a sex cross age where age is bucketed into 4 buckets? Or should we release a sex cross age where age is bucketed into 9 buckets? Or should we release a sex cross age where age is bucketed into 23 buckets? And for each of these, there is some sort of expert determined threshold. And so what we do is for each population group, we compute a noisy estimate of its size and see which threshold it falls under. So 19,000 is less than 20,000. So therefore, we decide that for this population group, its statistics are released with sex cross age with 4 buckets rather than 9 or 23 buckets. And so that's how we do this for every population group. And the final optimization is that some population groups we already know are really, really small. Like experts know that these are really small population groups based on prior censuses and ACS data. And so rather than doing this adaptive computation, we just decide that the only thing we do is a total for those population groups. Okay, so putting all of this together, this is like the full algorithm that is run for each population group in the US. You can look at the link to the full paper is on the slide. But basically, if your population group is a total only population group, then all we do is release the total for it using all of your privacy budget. Otherwise, we do this 2-step adaptive algorithm where we first get the total count, and based on the total count, we compare it to a threshold, and depending on which threshold it passes, we either release just the total count or a sex class age with 4 buckets or 9 buckets or 23 buckets. Okay. So these are the noisy measurements that are being generated. Now, once these noisy measurements are generated, certain other statistics may be derived from these noisy measurements. So for instance, if we have released a sex class age, either 4 or 9 or 23 buckets, then we will get the total by adding up those counts, those noisy counts, as well as the sex marginal by adding up those noisy counts. And finally, the negative and really small counts may also be suppressed. And that gives you the full algorithm for the release of these statistics. Okay. I'm just going to check the chat to see if there are any questions. No. All right, that's good. Okay, so remember we talked about this privacy negotiation. Let me give you a very quick overview of what we did, how stakeholders thought about privacy laws, budgets, and these parameters. But basically, in any sort of deployment of differential privacy, there are 2 parties. There's an analyst who cares about the accuracy of the data or the fitness of use of the data, and there's a curator who cares about the privacy loss, right? To ensure that the privacy loss is bounded. And so often, like based on a prototype algorithm, the curator may say, hey, at the privacy loss budget we saw, you'll be seeing a margin of error of about 25 in counts. And the analyst may say, that's okay for national level counts, but for county estimates, that's too large. So can we increase the privacy loss? At this point, the answer could be no, we can't increase the privacy loss, but we need an intelligent way to sort of make progress, right? And so one way we could say is like, hey, we could devote more privacy loss budget to county estimates. Now national level counts will have an MOA of 50, where county level estimates will have an MOA of 11, right? And so on. And so all our algorithm optimizations were informed by this kind of stakeholder-informed privacy negotiation. And to help do this, we actually developed Excel-based tools to help stakeholders visualize this privacy versus fitness for use and make decisions about it. So they could specify fitness for use parameters, like, for example, margins of errors, and then see what the privacy loss budgets look like, but also see what the error in the final release statistics would be. And then they could modify these parameters and see what the impact is going to be on error. In this case, we were able to do this using analytical estimates of error and did not need to use the data itself. Okay, just sort of briefly on what does the privacy loss look like? Again, these are some targets that were set, but these are not the final margins of errors, accuracy targets. So the MOE target is half the width of a 95% confidence interval, and it's different for different population groups. So as you can see, when you have a detailed race category, the population, you have tighter privacy law, tighter accuracy bounds, but for larger population groups, we have looser accuracy bounds. And so that corresponds to a total privacy loss. You can back out what the total privacy loss is needed to achieve those margins of error. So for pure differential privacy, where you're adding noise in the geometric distribution, we could achieve a epsilon privacy loss of about 15.3. But with the discrete Gaussian version, we could achieve a row of about 1.41. Now, these seem incompatible, but you can actually put them both on the same scale by analyzing these algorithms under approximate differential privacy. As was described before, you get an entire curve. But if you pick like a delta of 10 to the minus 10, the failure probability, then the geometric mechanism algorithm results in an epsilon of about 13.2, whereas the discrete Gaussian gives you an epsilon of about 12.2. Okay. All right. So the summary of this part of the talk is basically the goal here was to release total counts and sex class age marginals of populations that are grouped by geography and detailed race and ethnicity. The fitness for use goals were that the error should be predictable and users will derive other statistics from the released ones. And so the algorithm that we designed has this adaptive design that helps limit error on small population groups. Okay, I'm going to check the chat to see if there are other questions. Salil's question was in optimization 2, it seems to have an opposite philosophy of the top-down algorithm, where you didn't want to pay accumulated error for aggregating low-level counts. Can you say anything to help reconcile these two different choices? I think that's a very good question, Salil. The only kind of aggregation we are doing is going from a sex cross age pyramid to a sex or a total, where you're basically aggregating either 23 counts or 46 counts, right? The error when you're adding up noisy counts, the error grows as the square root of the number of things that you're adding up. This is not too big. And so, so therefore, like the stakeholders felt like that is acceptable error compared to like spending privacy budget on those intermediate counts as well.
Thanks. And you guys, that's a contrast from the top-down setting?
Yes, it's a contrast because top-down, the fan-outs are so big, right? Like, you know, there are only 3,000 counties and there are like 80,000 tracts, right? So like, it's so much larger that you have to spend some budget at the county level. Otherwise, you're going to get noise when you go from tract to county. Yeah, that's right. Charlemagne's question is, do this approximate epsilon take into account the post-processing that utilizing expert knowledge, which does not seem to be protected by using the post-processing theorem? Everything that I described right now does not utilize any expert knowledge. So the privacy negotiation that I mentioned did not look at the data. It was just looking at empirical estimates of error or old data. So these approximate epsilons don't take into account anything other than the differential private algorithm. Hope that answers your question. I can answer it offline. There's a question about demonstration data products. There was a blog post yesterday about detailed DHCs, so please read it. Okay. All right, so I'm going to quickly try and talk a little bit about the second data product, which is called Supplemental Dhc. So till now, when we talked about these differential private algorithms, we were looking at one type of data. We were either looking at the person record, where you have properties of a person, or you are looking at a unit record, which is properties of households. And your algorithms are basically trying to take that one data set of that one schema and then generate statistics from there. But there are several tabulations that count persons in households that satisfy conditions both on the person attribute and the household attribute. So what do I mean? So you have a person record, as I mentioned before, you have sex, age, relationship to householder, a bunch of race and ethnicity codes, and a link to a household, which household they live in. And the household unit record has a mapping to a geography, and it has attributes about the household. It has race characteristics of the householder. There's a property like household type, household size, and so on. So these are not properties that can be associated with one person. These are attributes of the entire household, right? And there are several tabulations that require you to look at both the tables in combination. So if you want to compute, for example, average household size by age of person, or you want to look at household type by relationship for population under 18 years, You need to join both of these tables and then compute your statistics. All of these tables are iterated by geography, and some of these are also iterated by the major Hispanic origin and race groups. So here is an example of one of these tables. So your universe is population who live in households, and this population is under 18 years. And then you get a total, but you also look at the population, whether they are a householder, a spouse, or an unmarried partner, whether they're an own child that lives in married couple families, and so on. Now, what is different about these tabulations compared to everything you've seen till now? As I said, the statistics depend on the join of both the person record and the unit record. These join queries have a high sensitivity. What does that mean? So one person can not only impact counts in several tables, but also they can impact the magnitude to which they contribute to these statistics by more than one. So in particular, if you look at these two neighboring tables, in one case, there's a household that just has a householder and a child and a spouse. In another world, this household only has a householder and a child. Now, the entire household type for this household has changed from a husband-wife household to a single person household, or a married household to an unmarried household. So when you actually do the statistics, you can, in the first case, you will count 3 people going towards a married household, whereas in the second case, you get 2 people going towards an unmarried household. So one statistics goes down by a count of 3, another statistics go up by a count of 2. And so therefore, what is happening is like adding or removing one person in the original database can change your output statistic by up to 2 times the size of the maximum household, or the size of the household they are in. And unfortunately, there's no a priori bound on the size of the household. So therefore, making a differentially private algorithm that can give you a tight bound on privacy becomes hard unless you have some bound on the household size. Okay, so the algorithm that is being proposed here is pretty straightforward, but it has some important characteristics. So the first thing it does is it restricts the population to the table universe. The next thing it does is it actually joins the household record, the person record. So it appends the household attributes in the unit table to each record in the person table. But at the same time, it limits the number of persons in a household to some pre-specified truncation threshold. And finally, it computes a noisy statistics, either using a noise from geometric distribution or a discrete Gaussian distribution. As before, geometric distribution gives you pure DP, discrete Gaussian gives you 0 concentrated differential privacy. But the important thing is this truncation now. So the number of universe records per household is now bounded by this household truncation threshold, which means that some person records in a household may be dropped at random to meet this truncation threshold. And therefore, the statistics that will be reported will be an undercount and hence biased. The reason we are doing this is that if this truncation threshold is high, then you have to have more noise, which means you get more variance. Whereas if you have a smaller truncation threshold, you have some bias, but your variance reduces because you don't need to add so much noise to hide the contribution of a record. Okay, there's a lot of ongoing work with this data product. The privacy on negotiation is still ongoing. There's ongoing research and engagement with stakeholders to figure out to optimize this algorithm and to choose some algorithmic parameters. Like in the previous example, a previous algorithm, PHC may be modified to adaptively choose which statistics to publish. In this case, we expect that we may not be able to release accurate measurements for really small population groups. And so there's an effort to develop a principled model-based approach to produce estimates for small area as a post-processing step. And to summarize, again, here the goal is to release statistics that are dependent on both person and household attributes. These have a high and potentially unbounded sensitivity. And the key feature of this algorithm here is that these households are to be truncated to bound their size and sensitivity of the statistics. So the resulting counts will now both have some bias, but also variance. And the variance is lower because of the bias that is being introduced. And in ongoing work, we are still sort of figuring out how we're still iterating on the algorithm parameters and working on model-based statistical post-processing to estimate error in small area nodes. That's it. Thank you. Please feel free to ask me questions.
Thank you so much, Ashwin. I know you have to go, so I don't know if you have done a great job picking up the questions along the way in the chat. If you have 2 minutes to spare, I would ask if any of our in-person audience members have a question for Ashwin, maybe quickly. Sasha.
Hi, Ashwin. Thank you so much for a really great talk and for working on very important problems. On the first algorithm, you said something at the end, you may need to do some suppression. So as far as that particular step in your algorithm, do you report the % of that suppression? Is that very clear? Or how does this fit within formal privacy? Yeah, go ahead. You know what I'm asking.
Yeah. That suppression is basically completely post-processing. So if the Census Bureau decides to suppress it, like there's nothing stopping them from releasing these noisy measurements and then say only use those measurements that are greater than a threshold. But yeah, I think there's nothing stopping them from releasing what are suppressed and what fraction was suppressed and so on. That answer your question?
It's working, sorry. Yes, I just wanted to know, suppression has been around. So when we say suppression these days, with respect to the algorithms you're developing, what does that mean, right? Do we, do we report the % of suppression or not? And, is that going to be transparent, et cetera, right? So because that's very important.
It's going to be transparent.
Yeah, that's great. Thanks.
Well, in the interest of time, Ashwin, thank you again so much for this detailed walk over the detailed DHC files. I think there are more questions for you in the chat, but I think we can definitely forward those to you later to your email, and you can pick them up with the questions. Thank you very much, and appreciate your attention.